Hello, welcome to a video lecture on superposition and interference. In this video, we're going to be talking about topic 4 waves, specifically 4-4 wave behavior, and some of this information also comes a little bit from 4-3. The equations we look at though all come from 4-4. Alright, first thing we're going to define the superposition of two waves. Make sure you have this definition in your notes. And essentially, superposition just says that when two waves, or wave pulses, we should say, meet at a point in space, their displacements add together, and we get what's called the resultant wave, which has a displacement equal to the sum of the two displacements. This picture over here, I think, is pretty helpful. It kind of represents the demonstration we did in class with the slinky, where we created two pulses that are moving towards each other. They get closer together, and when the two pulses hit the same spot in space, we saw their displacements added together. So for example, if each wave here had a displacement of 1 centimeter above the equilibrium line of this slinky, when they come together, we get one pulse that for a short time has a displacement of 2 centimeters. The displacements add together. Something else interesting that happens is then the two waves continue to move apart and move through each other almost as if they forget that they ever combined, and they'll flip positions and keep moving. The superposition, though, is all about this. It's all about when the waves are at the same spot, their displacements add together and we get a new resultant wave with a total displacement. So there are two specific types of superposition that we need to look at. The first one is called constructive interference. And again, this is a special type of superposition, so it happens when two waves meet with their crests and troughs all lined up. What this means is we get a wave that has a larger amplitude than either wave individually had. So we can look at an example here with the graph of a blue wave and a red wave, and we have to imagine the blue wave and red wave on top of each other, and their displacements at all points on the wave will add together. So what that means is, now we have a versus time graph here. This could also be a versus distance graph. It would still work the same way. But so we can look at this time when we have our first two crests. The crest of the red wave has a displacement of about 1. The crest of the blue wave has a displacement of about 0.5. And so when we add those two displacements together, we get a resultant wave pictured here with a displacement of about 1.5. The fact that its displacement does matter because the sign, positive or negative, will matter. And so when we come over here, we see a displacement on the blue wave of negative 0.5, a displacement on the red wave of negative 1. So when we draw the black wave to represent the superposition of those two red and blue waves together, we get negative 1.5. They just add. Two negative numbers add together, we get negative 1.5. You can also see, since these waves are right on top of each other and in phase, their zeros also line up. 0 plus 0 gives us 0 here. So we get a resultant that's one wave bigger than either of the individual waves. We call that constructive interference. The two waves are helping each other out, so to speak. Right? They're constructively adding their displacements together. The opposite case is also true. We could have something called destructive interference. And this essentially just means we have two waves that meet out of phase. Their crests line up with their troughs line up with their crests, and so you end up with a very small amplitude wave. Here's another similar example with a red and a blue wave adding together. The red wave now at this time has a displacement of 1. The blue wave has a displacement of maybe negative 0.75. And so when we add those together, we get a displacement of something like positive 0.25 for our resultant wave, here sketched in black. We can see this is true because we have the red wave is like a positive sine wave. The blue wave is phase shifted 180 degrees, if you want to think of it that way. The blue wave looks like a negative sine wave. So in all cases, the crest of the red wave matches the trough of the blue wave. Come over here, the opposite's true. The crest of the blue wave matches the trough of the red wave. So again, in like 5 seconds, we have a displacement of about 0.75 for the blue wave. That's positive. And a displacement of negative 1 for the red wave, which gives us a total negative 1 plus 0.75. We get about negative 1/4. And so we can see that this resultant wave is much smaller in amplitude than either individual wave that created it. You can also imagine if the blue wave were bigger and they were the same size, we could get total cancellation. Here the red wave is a little bigger than the blue wave, but if this was -1 and +1, we would still get 0. So that'd be a case like this, where we have two identical waves that are just phase shifted 180 degrees. So since these two waves have the same amplitude, if they're 180 degrees out of phase and a peak lines up with the trough, or a trough lines up with the crest, all along the wave we would get total destructive interference, and it would be 0 intensity, 0 amplitude, all along the wave. When we're talking about destructive interference, to be honest, this is usually what we're talking about, is totally destructive interference. Technically, any case like this is destructive, but this is what most people are talking about when they say destructive interference, complete cancellation. Okay, so the rest of the lecture is really about what causes this interference, and we usually think of this in terms of a path difference. In most problems, we're looking at waves in space that move from two separate sources. And so path difference is what you want to think of as what causes constructive or destructive interference. Path difference is defined, it's what it sounds like. It's the difference in the distance traveled by each wave from its source. So we'll try and make a sketch and think about that. Here we have two speakers, again, kind of like the demonstration we did in class. Now the speakers, remember, are creating sound waves, which are longitudinal waves. And we should mention that everything we just said about crests and troughs can be said for compressions and rarefactions. It's going to work exactly the same way for a longitudinal wave as for a transverse wave. So the way that they're sketching it here is we use a dotted line for rarefaction, a solid line for compression, and so on. So we can see the one sound wave here that spreads out from the speaker on the right, the other sound wave here that spreads out from the speaker on the left. And it turns out when we have a compression from the first speaker meeting a compression from the second speaker, we get constructive interference. All these little dots represent constructive interference. So compression on top of compression is just like crest on top of crest. Also, rarefaction on top of rarefaction is just like trough on top of trough. So all these spots give us constructive interference. We're going to look at this one specifically and think about that. Constructive interference in this case would mean you could stand here and hear a loud sound. The two waves add together constructively and you get a very high amplitude, which remember means very high intensity. So let's say you're standing at this point, you're distance D1 away from the first speaker, and you're distance D2 away from the second speaker. The two waves are identical. Usually we attach them to the same source, and so they're creating the exact same sound wave. One has to go further than the other, though. So if the distances are different and you're still getting constructive interference, you'd want to think about why. And to define them, if the path difference is an integer number of wavelengths, there's constructive interference. So you can try to visualize this, but if the wave from the second speaker has to go D2 is like one wavelength further than the wave from the first speaker has to go, they'll still arrive in phase. But if it was a half integer number of wavelengths, we would get destructive interference. So if this wave had to go 1.5 wavelengths further than this wave, they would arrive out of phase. You would get destructive interference. We're going to look at that in a little more detail coming up here. This is a image that I think will be helpful to kind of visualize why that happens. Same sort of deal here. We have two sources, call them S1 and S2. The source S1, let's say, goes to this point in space. S2 also goes to that point in space. And so when they meet, we think about what type of superposition we have, what type of interference. S1 travels 6 full wavelengths to get to that point. We can see 1, 2, 3, 4, 5, 6 crests in distance. So it goes 1, 2, 3, 4, 5, 6 crests. The red wave needs to go 8 wavelengths to get to that point. And obviously the red wave travels further, but because it's just exactly 2 extra wavelengths, those extra two crests really don't matter very much because they still arrive completely on top of each other, completely in phase. And so when they meet, the crests will line up with the crests, the troughs will line up with the troughs, and so on. So you get constructive interference at this spot. Try and imagine, and it might be helpful in your notes to make a sketch, what would happen if this wave went 6 wavelengths, but this one went, say, 7.5 wavelengths. You can try and make a sketch, and hopefully you can see why, in that case, the crests will line up with the troughs will line up with the crests, and you would have destructive interference. The equations in your data booklet that represent this are listed here. So we say for constructive interference, the condition is that the path difference be an integer number of wavelengths, which means n times lambda, where n is an integer, like 1 wavelength, 2 times a wavelength, 3 times a wavelength, so on. N can also be 0. There can be, which would just make this whole term 0. The path difference would be 0. And for destructive interference, like we said, we need a half integer number of wavelengths. So this is how we deal with that, n plus 1/2 in parentheses, which means I could have 1.5 wavelengths, 2.5 wavelengths. If n is 0, that would just be 1/2 of a wavelength. Do make a note, these equations do assume that the waves are emitted in phase. If they were emitted out of phase, these equations would actually flip. So we're assuming that the waves, when they're emitted, the peaks are emitted at the same time, the troughs are emitted at the same time. The IB can ask you questions where they're emitted out of phase, and you do have to think about that. So these are very conceptual equations. They do rely on you making a sketch, thinking about how the waves are emitted and what will happen when they meet. But they're really useful reference in your data booklet. Okay, so we're going to apply that to try and think about what's called two-source interference. In this case, we're going to have two sources, call them S1 and S2, separated by a distance d, and they are also a distance capital D away from this vertical line, which we sometimes will call the screen if we're looking at specifically light. But they're distance capital D away from where our detector, we say, will be. And we know from class, again with the speakers, that if these were two speakers, say, emitting sound waves, along this line you would move and hear a loud spot, a quiet spot, a loud spot, a quiet spot, a loud spot, a quiet spot, and so on. Those correspond to areas of constructive and destructive interference. And so what that's called is an interference pattern, where you have a regularly spaced areas of high intensity and low intensity because of constructive and destructive interference. So that's what we need to look at with this two-source interference. So we're first going to look at a point, we'll call it O here, which is sort of halfway in between the two sources, but along this line. And if we want to look at what happens there, remember it all comes down to the path difference. So we're going to use two rays to trace the path taken by the waves from the two sources. So the red arrows represent the rays, the wave that travels from S1 to point O, and the wave that travels from S2 to point O. We want to think about the path difference. That'll tell us about the interference. In this case, the path difference is 0. You can hopefully see by symmetry, the two rays should have the same length if this is exactly halfway in between. And so with the path difference of 0, that corresponds to n equals 0, our first equation in the data booklet where we have constructive interference. In other words, that would be a maximum intensity spot. For the speaker demonstration, for sound waves, this would correspond to a loud spot. If we had two sources of light, for example, that would correspond to a bright spot. But just a maximum, we call it. That's the one special spot where you have some symmetry. Anywhere else we choose to go, there's going to be a path difference. So let's look at a point P up here, some distance away from the center. Again, we'll draw two rays to represent the distance that the wave from S1 goes and the distance that the wave from S2 goes. We can see here S1 does not have to go as far as S2. So there is a path difference, and we're going to use some trig to try and think about the path difference. We'll make an angle theta down here, which is the angle between the ray and a horizontal line. We do have to make some assumptions when we do this. Mainly, that the angle is going to be the same for both rays, which probably doesn't look true here because we're drawing this kind of zoomed in. It's not exactly to scale in the way you'd normally see these problems. S1 and S2 are really usually much closer together relative to this total distance d. All right, usually capital D is much bigger than lowercase d, but we're drawing them sort of spread out so we can see the way these angles work. Okay, so we need to think about the path difference between these two waves. What we're going to do is create a little right triangle here. And there's some alternate interior angles going on. You can try and work those out yourself if you're interested, but just know that this angle here is the same as the top angle in this right triangle. The reason we do this is because, okay, we make a right triangle here, so we drop a line from S1 down to the ray created by S2 so that we hit that ray at a 90-degree angle. We create a little right triangle here, and then you can try and imagine the corner of this right triangle from there to point P is the same distance as from S1 to point P. You can imagine taking some scissors or something and snipping this ray right here, and then you could drag it up and it would have the same distance as from S1. So we create this right triangle because this little leg should be the path difference. This leg is the extra distance that the wave from S2 needs to go as compared to the wave from S1. So the small leg of that right triangle is the path difference for those two waves. Meaning we have a right triangle where the leg is the path difference we're interested in, and we also know the hypotenuse is lowercase d. That means we can do some SOHCAHTOA, some trig, and say that the sine of the angle is the opposite side divided by the hypotenuse. So the sine of this angle must be the opposite leg, which is the path difference. Here we just write PD for path difference, divided by the hypotenuse, lowercase d, gives us a trig function that'll tell us something about the path difference. Here's another picture that's a little more to scale because we don't bother drawing the line capital D a distance away. Here we can see that we assume the two rays are parallel. And so the path difference is always going to be d sine theta. This angle here is the same as the angle between either ray and a horizontal line. So if we have our path difference d sine theta, we can then think about that in terms of what's happening at this point where the waves meet. If we know the path difference, we can talk about whether there's constructive or destructive interference where the points meet. We just picked an arbitrary point P, so we're going to choose to think about when point P gives us our next maximum. So we're just really looking at the point on the screen where we specifically get the next loud spot or the next bright spot, the next point of maximum intensity. Since this was a zero wavelength path difference, as we move up, the path difference will increase and increase and increase. And so the next time we're going to get a maximum is our first integer, where n equals 1. So our path difference will be 1 wavelength here. So the path difference is going to be 1 wavelength. We also know the path difference here is d sine theta. We're going to call S the distance between the central maximum and this first maximum here, where the path difference is 1 wavelength. So we're going to start doing some algebra. We'll take the path difference equal to d sine theta and set the path difference equal to 1 wavelength. Next we have to do some trig, and this one's called a small angle approximation. For small angles, usually we say less than 10 degrees or so, especially true for angles less than 5 degrees. The sine of the angle is approximately equal to the tangent of the angle, which is pretty interesting. There's some videos and things online you can look at if you're interested in where this comes from, or you can just plug it in your calculator if you want to check it for yourself. If you put in, say, the sine of 4 degrees and the tangent of 4 degrees, you'll see they're almost identical. Sine of 9 degrees, tangent of 9 degrees also works pretty well. So that's called a small angle approximation. And again, we're able to use it here because in any situation that you're really dealing with, capital D will be much bigger than lowercase d. Capital D will be at least an order of magnitude bigger than small d, usually much more. And so what that means is these angles are really very, very, very small. So again, we're kind of stretching things out here so we can see the way that triangles work. But since the angles are usually small, we can assume that these are true. So the reason we do this is because if we use the tangent of the angle, we can define it in terms of measurements we already know. Remember, SOHCAHTOA tells us tangent is opposite over adjacent. So we got to imagine a right triangle like this, where the opposite side has a length lowercase s, and the adjacent side has a length capital D. The hypotenuse we wouldn't know, but since we have the small angle approximation, we don't need it. We'll just use tangent. So we're going to combine these equations. Well, the sine of theta we'll say is about equal to the tangent of theta, so it's s over d. So we're plugging that fraction in for the sine of the angle. And then we're simply going to solve that for s. We get this equation, and this is your two-source interference equation from the data booklet, where s is the spacing between maxima, or the distance between maxima. Lambda is the wavelength of the source, the wave that's creating the interference patterns. Capital D is the distance to the detector, or we should really say the distance a lot of times to the screen. We're talking about the line that the detector can move across. Again, the detector could be something like your ear if these are sound waves. And lowercase d is the distance between the sources. These are all distances or a wavelength, so they're all measured in meters, and you should be able to look at the equation and convince yourself that that works out. So as we said, what you get here is an interference pattern. And if we kept going, we would go up to a point where we had the next loud spot where we had the next integer. So this would be a 2 wavelength path difference. And so we have all these different areas of maximum intensity, which we call maxima. We also, in between the maxima, have quiet spots or dim spots, areas of minimum intensity. And so as you move along the line, you hear loud, quiet, loud, quiet, so on. The first minimum, for example, if we came up as the path difference increases, this would happen when there was a half wavelength path difference. The first maximum, we have a 1 wavelength path difference. Here we would have a 1.5 wavelength path difference. Here a 2 wavelength path difference, so on. There's a lot of symmetry going on in this problem and in these two source interference patterns. And so in that equation, we define S as the spacing between maxima. That's because they're evenly spaced. They're all spread out by the same distance. So we can label all of these as S, the distance between any two adjacent maxima. And the minima are right between the two maxima, so it should make sense too that the distance between two minima is also S. All right, so you just want to make a note that the maxima and minima in a two-source interference pattern are evenly spaced, which makes that equation easy. You could, for example, find the distance between the central maxima and the second. We usually call this the second maxima, the second one up from the center. And so you could find the distance between this guy and this guy. It would just be 2s. And so that's the math behind the two-source interference pattern. Again, the really important thing here is the path difference being an integer wavelength or half an integer wavelength, and trying to think about how that creates this interference pattern of maxima and minima. This equation comes up a lot in a lot of different problems. The IB has said that you will not need to derive it. So some of the details in the trigonometry, the small angle approximation, trying to imagine these two lines as parallel, that's not the most important thing in the world, because you're not going to be asked to replicate this math. But it is helpful to make sure that you can follow along, understand what's happening, especially in terms of how the path differences create this interference pattern. We'll get into this in a little more detail when we do the double slit experiment and talk about what happens for this with light. But again, this equation will work for any two-source interference problem. All right, thanks for watching.